Good afternoon, everybody. Welcome to the final design review for Team Guardian. My name is Parag Kipla, and I'm the team lead. To my right, I have Aaron Piggott and Steve Morwilson. So just an overview. This is basically a multidisciplinary collaborative engineering project that Boeing is putting on. Boeing is in charge of this, and we have 5 schools as part of this as well. We have Embry-Riddle, Purdue, Georgia Tech, Tuskegee, and BYU, who is not part of this particular. This is Team Guardian. We have people from Georgia Tech, Embry-Riddle, Purdue, and Tuskegee. And these are our coaches, Dr. Khan from Tuskegee, Adam Haddock from Boeing, and Greg Kidd from Boeing as well. So we have a team structure that's set up where we have a team leader at the top, and underneath him we have chief engineer who's from Georgia Tech, chief editor who's from Georgia Tech, secretary who's from Purdue, and IPTs under the chief engineer. And we have IPT leads as well for those. So now I'm going to talk about the market analysis that we performed before we even got the conceptual design of the airplane. So initially we were given a set of RFP requirements from Boeing, but we weren't required to follow them. So they were basically giving us a couple of the missions that they thought we could do. We looked at those missions, mixed and matched a few things that we thought we could perform, and then came up with our own little mission. So we looked at the requirements such as loiter time and dash requirements that they had suggested, and we kind of came up with our own. Based on that, we started looking at the first responders. We made a criteria matrix of the first responders who we would be catering to. Found out that there were 2 in particular that we would be easily able to cater to and would benefit greatly with the UAV. So those 2 were the hot shots and the search and rescue teams. We ultimately went with the search and rescue team because the hot shots, we talked to the chief technologist for the entire hot shots of America. And basically he wanted something that would fly at 70,000 feet or 80,000 feet that would be able to look at all the fires at once and be able to help the firefighters out from a very high altitude. He also wanted something that would be easily available to the firefighters while they were flying, but while they were fighting the fires. But we realized that they would be too busy fighting said fire and not really watching the video feed from the airplanes. That wasn't really useful. But mostly because of the high altitude problem and the capabilities were just something that we could not provide. So we went to the search and rescue teams. So we actually talked to the search and rescue teams in Prescott, so we were very fortunate to be in this place. And in particular, the rural search and rescue team here. We had a really great interest in the community, and we realized that it would benefit them greatly because their whole description deals with the fact that they were trying to find someone using the cameras. So that would be something we could deliver. And it would be an interesting challenge because they wanted something that was multi-role and be able to disassemble and fit really quickly into some space requirements that they had. So there were 2 groups within Prescott Search and Rescue, the Jeep Posse and the backcountry. The difference mainly being that the Jeep Posse used vehicles to get around. So they have a larger space available to them to fit the airplane in. The backcountry, however, was a limitation for space because they would have to carry everything in pelican cases on their backs or somehow and transport them across distances and different terrains. So the missions were also different. Jeep Posse, since they use cars, end up taking on longer missions, while the backcountry usually is out in the field for about 2 days max. So we took that into account when we looked at their loads as well, because they have different packs. They have a 6-hour, 24-hour pack, and these are the weights. So we wanted something that was lightweight and they could carry around with them if necessary. They also operated in all sorts of terrain and all climates, which was an interesting problem for us. We had to solve that as well. So these are the top requests from the Jeep Posse teams and the backcountry teams. As you can see here, they have very similar requirements or needs. They wanted something that was portable and lightweight with thermal and visual cameras, with GPS functionality and auto return, so lots of autopilot functionality built into it as well. And Jeep Posse wanted something similar. They have 2 seasons, the fire season and the search season. We would have catered to the fire season, but it's very short amount of time compared to the rest of their function. So we catered to the search season, and they needed a camera, thermal camera, same thing, GPS, a radio relay, so they could actually extend their range of communication with our aircraft. And we wanted something that was had a small payload capability, which we initially looked at, but we decided to drop. And we wanted something with a minimum 60-minute flight time, which was our requirement after they said that. So first responder feedback. Boeing actually did a little survey for us before we even started. They went on LinkedIn and polled all the first responder groups on LinkedIn for what they would kind of want. So it's not search and rescue in particular, but deals with a whole bunch of not search and rescue, but first responder teams. So as you can see, it's very different. They wanted some visible camera and thermal imaging, but that's kind of where it stops for the most part. They go to chemical sensors, which we didn't have a requirement from search and rescue. But they also want something like autonomous return to base, which is something search and rescue wanted. So the top 5 for search and rescue were just thermal imaging, because they told us a story about how they go out and they find little children huddled on rocks, and they're the same color as rocks. And because they're so cold, they start to blend in with the rest of the environment. So they want something that would be able to pick that up as well. And then they wanted autonomous system, visual camera, reader, repeater, and they wanted something small and lightweight. So based on all this, we looked at conceptual design. So we started designing initially. We set a few goals for ourselves. For example, we wanted something long endurance and high-speed capable aircraft as well. That could also be flown on all sorts of terrain, so mountains and valleys and such, and then be location aware. And engineering goals, we had a few requirements such as fixed wing and hand launchable from Boeing, but the rest of it we came up with ourselves. They wanted something portable and lightweight, which we wanted to deliver. We also wanted something multi-platform and all-weather and hand launch and simple operation, because we wanted something that they could fly with minimal amount of training, since they're first responders first and not pilots. So these are one of the 2 mission diagrams we had set up. We just had this in particular where you launch from one location, fly around for 60 minutes, and come back to the same location, replace the batteries, and launch again. And the second mission diagram we have deals with you launch it from a certain location, you fly around, and then G-Posse or backcountry either meets you or you go fly to them, and they change out the batteries and you start flying again. So we came up with 3 conceptual designs, 2 of which are presented here right now. We came up with a very conventional aircraft where it was a high wing, a tractor configuration, and a conventional tail. And then we also came up with a different type of design, which would be a little bit safer for a thrower, which dealt with high gull wing, a pusher prop, and a conventional tail. But ultimately, we decided to go with the 3rd configuration, which is very modular and could be easily replaced. The pod itself can be replaced, the wing can be replaced to make it high-speed capable. We can move stuff around to change the CG as necessary, depending on the payload and the requirements. And this was a very conventional aircraft because we had a high conventional wing, tractor configuration, and a conventional tail, but it was also modular. So based on this, we decided to finalize it, and this is our final aircraft. This is our final design, where we have the pod here, as stated before, a wing, a conventional tail, and a tractor configuration. And right here is our camera system, which gimbals. And we've had, this goes forward and aft, so we can chase CG around as necessary if the payload changes. Next, I'll pass it on to Aaron, who will do performance and sizing.
Thank you, Parag. So I'm going to go through some of the performance, sizing, aerodynamic, and aerodynamic calculations that we went through in the creation of our aircraft. We began the sizing of the aircraft with traditional power to weight versus wing loading diagrams. Some of our requirements that we were looking at is we wanted high endurance for the aircraft. As we stated, we had a certain climb requirement, as well as we wanted to be able to do a 30-degree bank at our loiter speed in flight. Some of our assumptions that we made at the beginning of this process from prior DBF experience and prior manufacturing experience was a Oswald's efficiency of 0.8 and a CD0 of 0.04. We also used a propeller efficiency of 0.6 for our initial assumptions, and then we used for all other speed calculations where we used stall speed, we used the stall speed 5% over the original calculated stall speed for extra margin of safety. All of the components were designed for a max takeoff weight of 12 pounds, although we tried our best to shoot for a 10-pound aircraft. Here you can see our wing loading versus power to weight ratio diagram. We chose a wing loading of 1.8. We didn't want to go any lower because this would create difficulty for the first responder in hand launching the aircraft. We didn't want to go any higher for additional structural weight that would be needed to support the aircraft. From that we got a power-to-weight ratio of 21 watts per pound, and that gave us a planform area, projected planform area of 6.67 square feet. Now I'll go into a little bit of the aerodynamics. We began with the airfoil selection for our wing. We began with a large bank of airfoils and then narrowed it down to 9 based on high lift to drag ratio at low Reynolds number. We were at a Reynolds number of around 200,000, 2 to 250,000, and so that's how we selected the airfoil. We narrowed it down. We selected the SG6043 based on those requirements. However, that airfoil is very thin, and because of the small chord length of our aircraft, we ended up adding 10% thickness to that airfoil to ensure that we could carry all the components in the wing that we would be needing. So for the actual wing design, we began by selecting the aspect ratio. Higher aspect ratio means better endurance, and so we looked at aspect ratios of 7, 8, and 9. We didn't want to go any higher than 9 again, so that we would not make the hand launcher's life any harder. And we ended up going with 9 because we got the best endurance calculations in AVL from that aspect ratio. We ended up steering away from a rectangular wing towards what we call Schumann tips, where the outboard sections of the wing have a sweep or additional sweep in some cases. And so that was done to avoid tip striking on belly landing. So those Schumann tips also had some added dihedral. For the empennage section, we chose symmetric airfoils 0012s for both the vertical tail and the horizontal tail. We wanted to ensure that we didn't require too much elevator deflection at trim straight level flight, so we used that to help size our elevators, and we ended up with an elevator trim of 4.7 degrees at straight level flight, and we set a maximum of 15 degrees deflection for the elevator. CFD analysis was performed to look for ways to optimize the endurance of the aircraft. So we were looking for ways to reduce induced drag and do so by reducing wingtip vortices. So the CFD was run with a mesh that had 3 to 4 million cells. And the reason there's a range is because the mesh cell count would depend on the angle of attack that we were running the case at. We used a Reynolds number of 210,000, which is using air conditions in Prescott, as well as our loiter velocity. And we used the KO mega turbulence model due to its robustness with complex geometry in aerospace applications. Comparing these 3 wingtip, we used this to compare 3 different winglets, as well as the Schumann tips, to a rectangular wing. You can see here that how much the L over D increased with each wingtip device over the orange dots, the rectangular wing. And so we found that with the Schumann tips, which is what our design, our preliminary design had, we would increase the loiter endurance by 5.5 minutes, and the 60-degree swept winglets that we looked at would increase the endurance by 8.5 minutes. And those 3 different winglets, by the way, have fixed cant angles, fixed height. The wing and wingtip configuration has a fixed planform area, and we just varied the sweep to find the optimum sweep for those winglets at this low Reynolds number. Here you can see the reduced vorticity plotted on a plane a meter behind the trailing edge of the wing. You can see that the rectangular wing is the only one that has any red on the plot, so you can kind of see the back of the room. But all of these wingtip devices significantly reduced the induced drag caused by wingtip vortices. So of course, CFD is never a standalone way of looking at your aerodynamics, so we compared to the wind tunnel to try and verify the CFD. We had some problems with the wind tunnel. We were getting some very unrealistic numbers. You can see CD values of 0.25 at 0 degrees angle of attack. It's about 5 to 6 times as higher as we would expect. And so we initially were going to be doing the wind tunnel testing at Purdue. They ran into problems with their wind tunnel where they didn't end up having the speed that they thought they had because something in the wind tunnel broke, and so we switched here. So we ran out of time to troubleshoot the wind tunnel results, but that would be something that we would have done if we had more time. And next I will pass it off to Stephen to talk about propulsion.
All right. So for propulsion testing, we needed to verify our motor calc data with our wind tunnel data, all that incorporated motor and propeller. That was very important because we needed to make sure that we had enough static thrust enough to launch, but not too much to where it would be uncomfortable for our launcher. So if you look at the graph here, at about 75% throttle to 100% throttle, the data are in agreement with each other, which is nice. And so at 100% throttle, we're producing about 6 pounds of static thrust. However, we thought that was a little not enough thrust for a 12-pound aircraft, so we decided to switch the 12x8 propeller to a 12x6 propeller, and then increase the static thrust to about 7 to 7.2 pounds thrust, static thrust. So our electrical system subsystem incorporated the prototype tube, probe, the Prescott autopilot, a GPS, and a gyroscope. Another part of the subsystem was the camera and gimbal. Now the gimbal was a 2-axis gimbal, which allowed us to, which allowed the camera to view up, down, left, and right. These were controlled with another RC controller. And if you look up here on the top image, this antenna, this is connected to our front-person view camera, which would enable live feed video to our ground station and another person wearing video goggles. So for structures, we did bending, compression, and tensile tests. We used 2 different diameter carbon fiber tubes. We chose to do different tubes because we wanted to find a diameter that was sufficient enough to handle our aerodynamic loads. We found that a 1/2 inch carbon fiber tube was sufficient. We also did deflection testing on our new carbon fiber spar. We used 15 pounds and 22 pounds, and this rig allowed us to apply those loads onto our new spar. So the 15 pounds was chosen because that's how much force our aircraft would experience during stage of the flight, and 22 pounds because that's how much our aircraft would experience during a banking maneuver. And that 22 pounds is our maximum load limit. So for the 15-pound load, the spar experienced a deflection of about 0.625 inches, and the 22-pound load deflected the spar about 2 inches. So here you can see a drawing of our entire aircraft, and note that our pod here is able to move forward and aft, and in respect to our CG location. So this piece here is what we use to connect the 2 wings together, and also to connect the wings to the rest of our aircraft. We call this piece the bulkhead connector. So at first, when we printed out the bulkhead connector, we printed it as one solid piece, and it came out way too heavy. It was about 2 pounds. So what we did was we went back and we hollowed out as much as we could. That saved us a ton of weight and reduced printing time quite a lot. Another key thing to notice are these holes, 1, 2, 3, and 4. that's where the spars of the wings would enter and attach to. Now, because the spars are tubes, we're able to insert aluminum rods or stiffeners, and that would help with deflection of the wings, for the wings, decrease deflection of the wings. Manufacturing. So the first things that were manufactured were our wings and empennage. We used a hot wire CNC cutter to cut out our wing profiles, and then from there we fiberglassed them and put them in the vacuum bag, and it came out really well, really nice. And the same process was done for our empennage. Our payload pod was manufactured with a 6-inch diameter carbon fiber tube and a 6-inch diameter clear dome. Now the carbon fiber, the payload pod was reinforced with laser cut wooden structures, which helped stiffen the payload pod. And those stiffeners also acted as a standoff, which helped, which also doubled as the point where we could put our electronics or mount our phone. Testing. All right, so our first flight test went really well. It flew with bare minimum components. The pilot told us that it was very easy to fly, and that once trimmed properly, it pretty much fly itself. Although one thing to note is that our rudder needed a large amount of trim to fly itself flight, and that's probably due to a few things. One being when the rudder, the vertical tail was attached offset from the center line of the aircraft. And another reason is that while manufacturing the vertical tail, the camera was added to it unintentionally by itself. So after the flight, we found out that there was a 300-watt power draw from the battery, and from that we could estimate that we could fly about 23 minutes, and that's just on one battery. Our original plan was to fly with 2 batteries. So with all the data we had, we predicted that we could fly about 45 minutes. So the second test flight was to test the functions of our autopilot. And one of the functions that we tested was stabilize mode. So a little background behind stabilize mode is that once you turn it on, the autopilot tries to trim the aircraft to fly at a scheduled flight. But we didn't take into account what default was in the autopilot. So when it was in the air, we switched it on, it just died. It went down. It dived down. But luckily, we had a really good pilot, and he was able to recover from the maneuver. But because of that maneuver, there was so much force that the aluminum stiffeners permanently deformed about 10 degrees on each side. Here's a video of our flights.
So it was like drizzle, so we did test our all-weather capability. This is a Georgia Tech just a few weeks ago.
Georgia Tech last Wednesday.
That's Wednesday. Well, it feels like 3 weeks.
It just seems like weeks.
Just going to fast forward until the landing portion of the flight. Show that.
nothing went wrong. So here are some stills of our during our flight. All right. So our first test flight, our first attempt during fly off actually did not go well. It crashed, and with further investigation, we found out from the crash that the battery had a dead cell in it. So we were only running at 75% power, and 75% power was not enough to get our aircraft to launch properly. So we had to do, and that was at 12 pounds. So what we did was go back to the aircraft and took out the camera gimbal system and the autopilot, and it brought down the weight to about 10.5 pounds. So now, so that video you just saw was our second flight attempt. So during flight, hearing back from our pilot, going back to the pilot, it was very easy to fly, not very hard, didn't have to put too much work into it. Sea level flight was good. Another thing we noticed, found out, was that we didn't need as much elevator deflection to trim to fly sea level, to fly at sea level flights. So that was actually kind of nice. I will now pass it on to Rob, who will talk about project performance.
So we were allotted $8,000 from Boeing. We didn't end up using it, mostly because we were going to initially buy a thermal camera to use, but then we strongly recommended by Boeing not to buy such an expensive component, which was a few $1,000s for single use. So we ended up freeing up a lot of our budget. But we did end up using about $1,400, $1,500 for structures for the actual material for our airplane, and then around $1,300 for electronics, since we had the camera as well as batteries, etc., autopilot system. And we only used about $220 for propulsion for a motor and such. So there were quite a few benefits of this project. It was definitely a learning experience, to say the least. Some of the benefits were definitely trying to deal with multiple time zones as we would in a large company. So that was challenging even within 3 time zones. And there were multidisciplinary teams which would exist as well in large corporations. So we had a few electrical people and a few mechanical people, propulsion engineers and such, and we had to deal with battle aerodynamics and propulsion and such, so that was interesting, constructors. And then we also noticed quite a bit of different approaches from every university. There were some that were very hands-on, some of them were very conceptual. So trying to figure out who went first and who got to do what and take how much time was a challenge as well for our team leads and chief engineers. We did use quite a few communication tools. We had this text messaging app that basically we set up, so we had a group chat for the entire team, as well as small IPTs could talk to each other and figure stuff out, try to stay on deadline and figure out what the data was coming to. We did end up using Adobe Connect for a lot of voice chats. We would have used cameras, but we just realized that we didn't have enough bandwidth at certain universities, so that caused more trouble than it was worth, to be honest. But I'm sure that would have made a large difference in this project if we were able to see each other. Balancing individual personalities was difficult, to say the least. There were a few people who felt like they should take over the project, or some person wasn't doing it correctly, and trying to make sure that people were working together fluidly was very difficult. And the problem was that we only met once in Mesa, Arizona at the Boeing plant there. And we spent about a day, maybe 24 hours together maximum across 2 days or 3 days. And during that time, we had to judge each other's personality, figure out who would be team leader, because that happened a few days later. And who could be trusted and who would not be able to be trusted very quickly, which was, again, impossible, if you ask me. So identifying individual strengths and weaknesses happened after the fact, after we started giving a little bit more work to people, seeing how they performed, seeing if they got it done on time, what the reasons were, why they didn't. Based on that, we started to give more work and less work to certain people, and that became very apparent very quickly. Important lessons learned, definitely underestimating the importance of face-to-face communication. We met again at Georgia Tech last week, and that was very different because we knew each other by then. And just seeing each other and working together, because we had to finish this plane, we ran into problems, we crashed initially. It broke as we had designed it to. We had a single point of failure that broke just as we anticipated to save the payload, the delicate payload inside. That worked fine. But to get to that point, we were up till 4 a.m. or something, and the people we initially had trouble with during these meetings were actually very different in person. And I think that, I'm glad that ended a nice package for this project, because it was a very different feeling than it was initially. And then being considerate of other members' schedules, that was very difficult, because we ended up figuring out that we only had 1 hour on a Sunday night every week that would work for everybody across all the time zones and different schedules. So that's what we had to pick. And every night we would have 1.5 hour meetings as necessary. And that was very, very hard, especially if you have a test Monday or you have other work to do. And people were balancing school with this project, so that was challenging. Improvements. So BYU was kind of the subcontractor for this, and they ended up doing a lot of the planning and scheduling for this project. So recommendations I would give for this project were basically, and this is from a team leader point of view, trying to figure out increased organization, because the expectations weren't clear initially. For example, the RFP that we talked about, they gave us a few options, but they never said pick one, stick with it. And we didn't know that. They didn't make it clear to us that we were supposed to do that. So when we started doing it, they didn't say anything, so we assumed that was okay and moved on. Also, lecture topics. We had multi-calc lectures and CFD lectures that happened after the fact, after we already learned it ourselves, which wasn't very helpful. And rubrics and guidelines weren't distributed initially in a very quick manner when we needed them. And certain team leaders talked to certain coaches who would give them different information than other team leaders would. And even within our team, we heard different things from different coaches, and we started wondering who was right and who wasn't. So that led to some discussion as well. And then overhead work, there were a few times where I felt like some of the work wasn't necessary and no one told us that we had to do it. Or they told us but they never expected it, but some people didn't and didn't get in trouble for it. And shift and focus was difficult because of how we're treated at Embry-Riddle, where it's mostly engineering based, and especially the prelim and detail teams here are very engineering heavy. So having a very different mindset from the actual overarching Boeing team who was leading this, the coaches and the faculty and such, about how engineering is taking like a second, I guess it's not as important as marketing or talking to first responders and such. But we did learn from that too. And we tried doing engineering ourselves and finding out what worked and what didn't, and going to faculty here as necessary to make sure we were on the right track. The hardest part was identifying what we needed to know initially in order to actually learn it. So we ended up talking to a lot of our friends in field and detail here, referring to the reports that previous field and detail teams have done and kept in the SDL, referring to those, looking up Raymer, his textbook. We actually started a little book club initially to start reading Raymer's and trying to figure out what we didn't know and how to design this. So that was very helpful, but challenging at the same time. So I just want to thank the Boeing Company and all the schools that participated, as well as Siemens, Scorpio, and CDAPCO, who gave us the tools to use. But I'll open up to questions if there are any.
Edward M. So, great job. I know it's not easy. I was extremely happy to see how well you took care of margins and learned the lessons of the fact that CFD is never ready. So the fact that you carried, even using very rational numbers for drag, optimal efficiency factor, prop efficiency factor, and then added an additional factor on top of your P-stall. Really smart. Weight margins, hey, we're shooting for 10, but we'll design as if it's 12 and aim at 12. What I didn't see was static margin.
Static margin was between 10 and 15%.
But then you have comments about you had to do some work to get the CD back in the right location, and you sold in static market. Why it wasn't there originally.
It was when we moved components around and had to pull components out, that's when we had to adjust. And we ended up switching batteries. And, yep.
That was a big thing. I just kind of expected to see the static margin calculation early, and then, hey, here's on the small aircraft we work on, we often do the very simple test of, put a mark on there where we think the CG is, calculate it out, and then suspend the airplane on the wing tips. Yeah. Great work. Yes. Difficult, I know it'd be hard working in some of those East Coast guys, so don't get bored very early.
My name is Eli Jones. I'm a flight engineer at JSF. Really nice job working on a collaborative team like this across multiple sites. I think it's really valuable, and you'll find as you go out into the workplace that you're going to do this all the time. Like, I don't think I've ever worked on a project where you're working on multiple sites. Really good job, starting with a blank sheet of paper and getting all the way through an airplane and fly. Some of my comments, I guess, quite a presentation. I would say be careful with some of your derived requirements. So you talked a lot about, it's really good that you went out and talked to your customer and figured out what they needed. But things like all weather, do you really need all weather? The more specific you can be with those things up front, the easier the design is going to flow out of that. So just be careful.
We did break it down, we just didn't present it, but we had wind requirements and such, and made sure that it would be able to, obviously if it was too windy for certain miles, we wouldn't go and fly, and then if it was too snowy, for example, in Prescott, we just didn't present it, but I understand.
Gotcha. That's good to hear. Yeah, because especially in an environment where you have engineers across multiple sites,
Right.
you put those requirements out there, somebody might go off in a different direction.
Yeah. Right.
So, with your design, it's clear, I think you guys made a design trade-off between the weight of the vehicle and sort of its ruggedness. Flying an airplane like this in a search and rescue environment, you may want to balance that a little bit more. And one of the things that struck me was that you have a requirement to fly in valleys, and that sort of thing also adds some additional challenges.
Right, you have to.
Things like GPS reception for your autopilot and additional weather considerations. So I guess more specific to that, you talked on one of the slides about the throttle for a minimum of the flight is 25%. Did you guys do the calculations to see excess power?
So that was Georgia Tech, I believe he did do that, because I remember seeing it during one of the presentations that we did. I remember, unless Steve here. Sorry.
So, and was you at test flight at sea level or?
Very close to sea level, yeah, outside of Atlanta.
So that's just something to maybe dig a little deeper on and see, because if you're doing search and rescue, it's probably going to be a competition and not at sea level.
Right.
So the performance of the airplane really.
All the performance analysis and aero analysis was done at Prescott Sea Level, because these were the first responders we were catering to, so it was done at least a mile.
Okay.
Yeah. So we had excess power at sea level. We were fortunate to fly at sea level, because if it had flown at BYU, it would still have worked, but it wouldn't have performed as well.
I think that's all I have. Really good job.
Thank you.
Yeah, well, I guess first, I'm David Fairway, I'm with Bowling Defense in St. Louis. So, great job, I really like what you guys did with your initial investigation of customer interaction requirements. I can't tell you how many times I've actually heard in the industry, companies have said, well, they don't like the requirements, they make our own, and they don't want a contract, and wonder why. So, great job on that, definitely want to cater to your customers, that's reason why. So,
a little bit about some of your structures. I would like to see a little bit more in terms of the layout of the structure, maybe a little bit more of a diagram, especially I noticed, I think it was your second flight test, you had band stiffeners. So I would definitely like to see kind of more of a diagram as to why maybe that was, maybe the spacing was too big, and that kind of stuff, just to maybe gain some insight into how that ever happened. But in regards to your testing, so you tested bending, compression, and tension on composite cylinder, was it, for the boom?
For the spars.
For the spars. So I guess of those three, which do you think was the most important test?
The bend test.
Why?
Because of the joint between the wing and the, what we call the bulkhead connector, and the force felt in the wing.
Yeah, that's what I know. But it's always good to, I guess, complete your testing to get a good sample size, as well as sometimes you may not be predicting that you need to do certain analysis and find out what you're doing. I guess from the results of the testing, what were some of the results you got? Basically, was I guess strong enough to withstand all your loading, and you guys do anything beyond that?
So 22 pounds was our max, and Aaron based that off of a turn, a tight turn, that we would be expecting.
30-degree bank at our max speed.
Right. So did you come up with like any factor of safety, I guess, based on your test results?
Right, it was 1.5.
1.5, okay. And did you, I noticed in some of the test results in the bending test specifically, it looked like you had kind of a wide range of basically, I think these are stress and deflection blocks. But it looked like you had kind of a wide range in there. Any consideration for knockdown potentially based on you use one of these weaker components, maybe that might break in flight versus if you use one of the stronger beams? So I'm assuming you guys bought this from the supplier. Yeah, so any consideration for type of knockdowns on that? Potentially, I guess, over design in the sense composites typically knockdowns just for that factor.
I don't think we applied it on kind of, we just said that factor safety, which we recommend.
I think it's fine for this application. It's just in composites, if you guys do work in the future, know that there are a lot of knockdowns, even beyond testing knockdowns that you kind of come up with. There's environmental impact, there's corrosion type properties and the like. And most of the time, after you apply these knockdowns to your composites, you tend to find out, might as well just it kind of depends, right? So, can you talk about the single point failure? You had a crash or landing and started actually broken.
Right, so we talked a bit about the pod and how it had the laser cut plywood, basically internal structure. So we took a laser cut plywood, cut a slot of the carbon fiber, the 6-inch diameter carbon fiber tube, and had the laser cut plywood actually extend past into a T-rail into our bulkhead connector. So we had a metal T-rail basically that was bolted onto the balsa wood, or not balsa wood, plywood. Yeah, so basically in case it did crash, the wood would snap and deflect all the energy, and it wouldn't actually hurt any of the sensitive components inside the 6-inch diameter tube, which is exactly what happened. As we landed, we threw it and basically fell with style. Came down and crashed pretty hard. The belly landed really hard, and we were initially very concerned about the electronics inside.
Right.
But then we realized that as our team member picked it up, the pod basically separated from the rest of it. And we just ended up gorilla taping the whole thing together after taking out the core components. But it didn't work as designed, and we didn't mess up any of the electronics inside.
So I guess, did you consider any of those type of design approaches for some of the other parts of the aircraft, like connections, empennage? Because as you said, basically energy dissipation in the grass, that's really what you want. You want that to go somewhere else. Typically, you want that to break structure, not electronics.
So initially we had planned where, for example, the empennage would be connected so it would just snap clean off, but we ran out of time and basically had to put stuff together really quickly, so it was a solid piece. But in the future we would end up doing that. For the bulkhead connector, I know that basically we just had those stiffeners that were acting as a single point of failure because those bent first before damaging any of the actual wings, the parts that would be hard to construct. and we ended up just taking those out, putting steel ones in, and it was okay.
We also had a 3-inch strike plate on the bottom of the tail to protect the tail if there was wind.
So on your, looks like you did a deflection test at 15 to 22 pounds. You got a little over half an inch deflection and about 2 inch deflection. Did you guys have any deflection lines?
Just wanted to make sure.
Make sure it wasn't like 5 or 6 or something.
Yeah.
That'll be the fail.
Oh, that's definitely a good test, especially for these smaller vehicles, especially for security. And picking that right size can be difficult to size for that, especially if you have a high-tech condition.
We overcompensated for the fuselage boom. We called it fuselage boom, the single bar that basically connects everything together. We picked that after realizing that Georgia Tech had built a plane that was about 3 times as heavy and still withstood the issue. But we did additional analysis on top of that to make sure it was okay.
Very good, yeah, good job pulling that guy. Lean on your resources like that. So I guess last couple of comments was, I noticed there's a picture on here, it's your first test flight, you guys, one was holding it, a couple of you guys around it. It looks very large compared to a person.
Right.
I know it only weighs 10 or 12 pounds, so decent to throw it. But did you guys have any issues with the hand watch, with how big and how long the wingspan is?
We only had one person throw it at all the test flights, and he didn't have any issues. But I will admit he was a pretty strong guy. So I'm not sure. It would have been nice to have one of us throw it and see how it handles. But we didn't really do it.
Yeah, I'd be interested to see. Just,
Yeah.
It's light enough, but once you start getting things away,
He was our propulsion guy, so he kept saying about how when they were initially testing it, all you had to do was kind of just throw it gently, and it had enough static thrust to just go up, no problem. So,
But on that test flight day, we had 75% of the launch power because of the battery.
So I guess the last thing was, kind of a joke that we have is trust no one. do your own analysis and verify it yourself. But no, it's good that you went through the team dynamics like that. You do have to trust your teammates and you kind of have to learn how to move around that, especially you're never going to go up to someone and say, hey, I don't trust your analysis. Right? There's ways around that. You have to be people.
we secretly did error analysis here ourselves just to make sure everything works, so I guess, yeah.
I mean, it's good to do that at the same time you do have to understand